The robot used a single belt and two motors. When both motors moved in the same direction, the robot moved right or left. When the motors moved in opposite directions, the robot moved forward or backward. When the motors moved at different speeds, the robot moved along angles. Our system used a PS3 camera to track the puck's position. The camera was not mounted vertically above the air hockey table, which resulted in a deformed image. Homography was used to flatten out the image. The camera's data was interpreted by our code, which located the puck by looking for a round object the size of our puck that was moving and was green. The puck's center was matched with a pixel on the camera's image. This pixel was then converted to an X and Y coordinate. Puck's speed and trajectory were then calculated. Our system then used prediction to determine where the puck would be at any given time based on its speed and trajectory. We also predicted if the puck would bank and where it would end up. The next three clips will show a robot blocking, shooting, and predicting a bank shot. Our Simulink models ran on our Kiva microcontroller to control our motors. The Simulink model received X and Y coordinates from the code that ran on the computer. The model then computed how many rotations each motor needed to turn in order to get to that position, and used a PD controller to determine how fast each motor needed to turn. The PD model received feedback from our motor encoders. The feedback allowed our PD controller to slow down and stop our motors as they reached our desired position. Our red microcontroller signals were sent to our green H-bridge, which amplified the microcontroller's signals to drive the motors. The H-bridge changed the direction of the current flow through the motors using MOSFET transistors to dictate if the motors moved clockwise or counterclockwise. The direction is dictated by the signal sent from the microcontroller to the H-bridge. You may notice that we used two integrated circuits. These chips were used for encoder feedback. The chips counted 116 times with each motor rotation and sent the motor count to the microcontroller serially. The ceramic capacitors connected to them ensured that the encoder stayed powered, even if the circuit's voltage dropped. Watch what happens when we put it all together.